Alright, so far we've used the state diagram and also and alternatively a transition table to introduce our finite automata. And now we should start looking at formally defining the finite automata so that we could work with them mathematically. We know that the state diagrams were easier to intuitively get a grasp of what the machine does, but now we are kind of turning our head towards defining formally what a finite automata should be. And the reason for that is actually there are two reasons for this. Is that the formal definition resolves any kind of uncertainties that we may have about several different aspects of our machine. So a formal definition basically gives us precision in terms of what exactly a finite automata is. For example, if you have questions about whether a finite automata can have more than one start state, or is it allowed to have no except states, a formal definition would give us that precision in terms of defining what a formal finite automata is. Furthermore, a formal definition provides us with notations. Good notations help us think and express our thoughts quite clearly when we are trying to come up with statements about these kinds of machines, about their computation, about equivalences with other kinds of machines, and also, in fact, about what kind of languages they accept or they reject. These will effectively, the formal definition will give us the notations to do so. If you look at the notation here for a formal definition of a finite automata, which I will explain shortly what it is you see that it's quite arcane. It's very detailed, and it looks very much like a legal document. And as I said, the two reasons that we have having notations, clear notations, as well as the precise descriptions, requires the definitions to be this detailed. So every single minute aspect of our definition should be completely precise, and details must be spelled out. So what is a finite automata? If you look at this previous slide, we notice that a finite automata is a machine that is made of several parts. One of the important aspects of this system is that it encodes what is called states. So there is a finite number of states that determine the control of this machine, or rather the structure of this machine. Also, the machine needs to have a set of inputs, or rather a set of symbols that it recognizes, or that sequences that are made of these symbols can be recognized by this language, or by this machine, or can be processed by this machine. So we need to have a set of states and also a set of symbols that the machine can work with. The third aspect of this machine is effectively rules of transition. So every single one of those arrows that point from a state into another state, or even into the same state, these are the rules of transitions. There are two little additional details that are important to define this machine. The starting state, the state from which the machine always starts processing whenever it sees the first symbol in your input sequence, as well as a set of states that can be tagged as states which the machine accepts, and we call those accept states, or some definitions call them final states. So if we count these number of things that are needed to define a finite automata, we see that we need a finite set of states. We need a finite set of input symbols that we can process. We need a set of rules that dictates the transitions between states upon encountering a symbol from the input. We need to have a state to start in, and we need to have a number of states or a set of states that we can tag them as accept states. So we need 5 things. In mathematics, when you have a sequence of 5 things, they're called a 5-tuple. Therefore, a finite automata, the formal definition of a finite automata, is a 5-tuple where Q is a set of states, sigma is a finite set of alphabets, and by the way, Q needs to be also finite. Delta is a transition function, which basically describes where each state goes, or where each transition leads from and goes to when you see a certain alphabet or a symbol from the alphabet. Q sub 0 is an element from the set of states that we call it a start state, and the big F is a subset which could be also equal to the entire set of states, and is called set of accept states. So effectively, we need to define a finite automata, we need to have 5 things. Q, a finite set of states. Sigma, a finite set of alphabets, symbols. We call it alphabet. Delta is our transition function. Q sub 0 is the beginning state or the start state. And F is a set of states as a subset of the Q. And it is called the accept states. So as you see here, this formal definition gives us everything we need. It is very, very precise. It exactly says what each component of a finite automata is, and even properties of it. For example, sets Q and sets sigma are finite sets. It also spells out exactly what happens according to this transition function. And I'll talk about this transition function a little bit more in detail as we go on. That spells out what happens with our state machine. And also, it specifies that you need to have one and only one start state. So you just pick any of those finite states, any of them, and you tag it as start state. And you also must have a set of accept states. Now, this definition also is precise because it also tells us or resolves any kind of ambiguity or any kind of questions we may have about a finite automata. Can finite automata have how many start states can it have? So according to the definition, it can only have one start state. How many accept states it can have? Well, according to this definition, F is a subset of Q. So F could be the empty set. No accept states. A finite automata that doesn't accept any strings is still a finite automata. It could have just one state, for example. F could be Q sub 0, right? Or it could be equal to Q. So a finite automata where all of its states are accept states is also still a finite automata. So as you see, this formal definition resolves all questions that we may have about really formally defining our finite state machine, finite automata. And as I said, we can only have one and only one start state. Now, 4 out of those 5 rules that we saw, or 4 out of those 5 elements of our 5-tuple, that is a finite automata that we saw, are quite literally easy, in that you have a finite set of states, nothing really to it. Finite set of input alphabet, nothing really to it. One of these states is start state, and a number of these sets, a combination, a subset of the set of states, will be selected as, or will be assigned as or accept states for for our finite state machine. The third element, actually, the middle element, the delta, is basically the important part, really, because the differences between many finite automata that even have the same number of states and accept the same or get the same input alphabet or even have the same start and accept set of states, their functioning, the control mechanism of how they work, is encoded within the transition function. So the delta is really at the heart of what's going on with our finite automata, and this is our transition function. So it determines the rules for moving in our finite machines. If you have a state x and a state y, and your finite automata has an arrow from x to y with a label from your alphabet, and let's call this label A, then what this means is that this piece in our state transition or transition diagram that we saw will be represented as something like this mathematically: delta of x comma a parentheses equal y. Okay, so what this is, x is your current state. In your finite machine, when you encounter an input symbol. So this will be, A will be your current input symbol. And Y will be your next state. So this formal notation, delta of x comma a equal y, effectively acts as a mathematical shorthand. It basically tells us that if your state machine is in state x and it reads A, it goes to state y. Okay, so the way that we will work with our formal definition of a finite automata, or rather a deterministic finite automata, is that we represent this transition functions either as a state diagram that we saw there earlier, or a table in which the rows will represent the states that our machine has, and its columns will represent the input symbols from the input alphabet. So then my delta function will be basically a function that would be from a cross product of a number of states and over my alphabets. And then the elements of this table will be my transitions. So delta of q sub 0 comma a, delta of q sub 0 comma b, delta of q sub 0 comma c. The second row will be delta of q sub 1 comma a, delta of q sub 1 comma b, delta of q sub 1 comma c, and so on and so forth. So finally, the last row will be delta of q sub n comma a, delta of q sub n comma b, and delta of q sub n comma c, and so on and so forth. Okay, so this either is a a state diagram or a state transition table will define my transition function delta. Now if you notice here, the inputs of my delta function are an ordered pair. So the input of delta, the range of delta, will be from the cross product of Q, my set of states, cross with sigma, my set of alphabets. This is very, very important. So the domain of my delta function comes from an ordered pair. So the input, as you see here, will be Q sub 0a, Q sub 0b, Q sub 0c, Q sub 1a, Q sub n, b, or whatnot. So these ordered pairs, the first element comes from Q, and the second element comes from sigma. As you see, then these will belong to the alphabet sigma, and these guys will belong to Q set of states, as we defined earlier. The range of this function, namely the output, comes from Q. So the range of your function, transition function, is a state. And as you notice here, these deltas, these will produce some Q sub something, some Q sub I. Okay, now that we have our finite automata definition formally set, we can use this notation from our formal definition to describe individual finite automata by specifying each part of the definition 1.5, the definition of finite automata that we described. So when you're given a transition table for a finite automata or a state diagram for a finite automata, and if you're asked to describe and to define this finite automaton, remember that your finite automata is actually a deterministic finite automata is a 5 tuple. It has 5 components: Q, a finite set of states; sigma, finite set of alphabet; delta, the transition function, which comes from the cross product of the set of states and set of alphabets onto the set of states. So each transition function will take 2 arguments as input and produce 1 argument as output, 1 state as initial state or start state, and a subset of your original states, set of states, to be determined as the final state or accept states. So according to this definition, let's go about and define our M sub 1, our finite automaton. So the finite automata M sub 1 is basically a 5 tuple: Q, sigma, delta, Q sub 0, and I represent it with a small letter indicating that this is just one state. It's not a set of states, and the capital F, or the big F, as the a finite set of accept states. So this is my finite automata M sub 1. I need to now define precisely each and every single one of these 5 elements. First, Q. Q is a finite set, and in my case, it has 3 elements in it: Q sub 1, Q sub 2, and Q sub 3. 2. The alphabet is sigma, and this sigma is a finite set of 2 symbols, 0 and 1. 3. I need to define my delta. For now, I basically just specify its range and domain, and then I'll formally define it after I finish up the other parts that are easy to do. So it's going to be a function from Q cross product sigma over the range of Q. But I still need to specify that. I'm going to come back to that a little later. The fourth element is my start state. So Q sub 0 is equal to Q sub 1, because Q sub 1 is the one that has an arrow pointed to it from nowhere. And finally, the set of accept states. F is a subset of Q. So it is a set, and it contains only one element, Q sub 2. One thing that is very, very important that for you to know is that Q sub 0 is a state. But F is a set of states. This is very important. For if you erroneously here say F is Q sub 2, this is wrong. Okay. Also, you can if you say Q sub 0 is set Q sub 1, this is wrong. Okay. So be extra careful when you're defining your finite automaton. Remember, I said that the formal definitions are very, very precise. See, even putting curly braces over Q sub 1 makes your definition wrong. Or forgetting to put the braces over Q sub 2 for the final for the accept states, the set of accept states, would make your definition wrong. One thing that you need to also remember is that the first element is always a set. The second element is also a set. This guy is a function of Q cross sigma over Q. And the last element is also a set. But this element is just an element. Or a state. It's not a set. So 3 of these guys are sets. In fact, actually 4 of them are sets. The accept state is not a set. It's just one state. Okay, so we did that. And now let's go and define our transition function. So our transition function is delta, as I said earlier. So we're going to just elaborate on this a little bit. That it comes from Q cross sigma over Q. And it'll be effectively a table. So the delta is a table from Q cross sigma. So these guys are sigma and these guys are Q. And the inputs are going to be just the elements are going to be from Q, which is a set. So over the set of Q, we've got Q sub 1, Q sub 1, Q sub 2, and Q sub 3. And then over here, I've got 0 and 1. So again, remember, these guys are members of Q, and these guys are members of sigma. Then what I'm going to do is I'm going to look at state Q sub 1 over transition 0. Which state am I going to go to? So if I'm in Q sub 1 and I see 0, I stay in Q sub 1. So therefore this element is going to be Q sub 1. If I'm in Q sub 1 and I see a 1, I'm going to go to Q sub 2. So this element is going to be Q sub 2. If I'm in Q sub 2 and I see a 0, I'm going to go to Q sub 3. And if I'm in Q sub 2 and see a 1, I stay in Q sub 2. If I'm in Q sub 3, I'm going to go to Q sub t either on 0 or on 1. So I'm going to go to Q sub 2 under both these conditions. To specify that this is a Q sub 1 is the input state, I'm just going to put a little arrow next to it. and then I'm going to basically underscore these guys, actually just the Q sub 2's. So I'm going to underscore the Q sub 2's just to remind myself that these guys are my accept states, but you don't have to do that in the formal definition because we already defined our final states, finite, our accept states and our start state up here. Another way to specify your delta function is to spell it out. So delta of Q sub 0 and 0 is going to be delta of Q sub 1. Delta of Q sub 1 and 0 is Q sub 1. Delta of Q sub 1 and 1 is, I say Q sub 1 and I write Q sub 2. So delta of Q sub 1 and 1 is Q sub 2. Delta of Q sub 2 and 0 is Q sub 3. Delta of Q sub 2 and 1 is Q sub 2. Delta of Q sub 3 and 0 is Q sub 2. And finally, delta of Q sub 3 and 0 and 1 is Q sub 2. So I can either define my transition function by just spelling it out or writing it into a table that defines exactly what my machine does. Before I move on to the next, let me just go about and clean these guys up for you, because then I'm going to put these on the slides. Q sub 1 and 0 is Q sub 1, and this is Q sub 2, and this is over 1 goes to Q sub 2. Okay, now that we have the definition of our automata, we can talk about what does it accept and what it doesn't. If A is a set of all of the strings that my machine M sub 1 accepts, then we can say that A is the language of machine M sub 1. Or if A is a set that some finite automata M accepts all of its strings, then we say that A is the language of machine M, and we also write it L parentheses M equals A. We also say that M recognizes A. One of the things that you need to remember to avoid confusion is that a machine may recognize only one language, but it can accept several strings. So the language is the set of all of those strings that the machine accepts. And also notice that the language can be empty if your machine doesn't have any accept state, or that no string is accepted by your machine. Then your machine still recognizes one language, namely the empty language. So now that we have defined the language of a machine, now we can go back and take a look at our state machine here and see what is its language. And we've talked about you thinking about what this language is, and now I will write and spell it out for you. So just to show you exactly what is going on with my machine accepts or ends up in an accept state when it sees a 1, right? So if it starts in Q sub 1 and it sees a 1, or if it starts in Q sub 1 and sees a bunch of zeros and then a 1, it accepts that string. If it also sees a 1 and then keeps seeing 1, then it will also recognize and accept that string as well. However, after it saw the last 1, if it sees a 0, then it pops out of the accept state. And then it comes back to the accept state if it sees another 1 or if it sees a 0. So let's see what exactly happens. So if it keeps seeing a bunch of zeros and then sees a 1, it accepts it. If it sees a bunch of zeros and then sees a 1 and then keeps seeing 1s, then it accepts it. In fact, if it just starts seeing a 1, then it accepts it. If it sees a bunch of 1s, it also accepts that. So all of the things that these languages, these strings have in common is that all of them end with a 1. So I know that my machine accepts anything that ends with a 1 so far. However, what happens if my machine, let's say that it saw a bunch of zeros, and then it kept seeing a bunch of 1s, and then it sees a 0. After it sees a 0, then it pops out of my my accept state, only to come back if it sees another 0 or a 1. Now, if it sees a 1, then it's basically back the same languages or the same strings. It ends with a 1, right? So the only two other times that this string of 1 and 0 is going to be accepted if the next symbol is a 0 or if the next symbol is a 1, right? So we already know that this is a part of these languages. Now, if you see a 0 and you're back in Q sub 2, and if you keep seeing 1s, then you're going to accept. However, if you see another 0, then you pop out of your accept state, only to come back to your accept state if you saw another 0 or a 1. So if you notice here, the only time that you pop out of your accept state is if you see an odd number of zeros after the last 1, right? So basically, if you want to think about this machine, is that it goes to accept state at the last 1. So if your string ends with a 1, you're in the accept state. Or if after the last 1 you see an even number of zeros. So the languages that your machine accepts is a set of all the strings W, such that W contains at least one followed by an even number of zeros. And this is the language of M sub 1. So the language of M sub 1 is the set of all strings that have at least one 1 followed by an even number of zeros. In fact, if your languages are composed of any string that ends in a 1 or ends in a even number of zeros after the last 1, and that is the language that the machine M sub 1 recognizes.